Hello everyone, in this video we are just going to interface 7 segment displays with our microcontroller STM32F44RE. Let's get started. So in this video we are just going to develop the base drivers required for printing some numbers onto the common cathode type 7 segment display with the help of STM32F446RE microcontroller. So now let us try to understand the schematic diagram that we are going to build for interfacing common cathode type 7 segment display with the microcontroller STM32F446RE available in Nucleo F446RE development board. And here you can see in the screen, this one on the left is the Nucleo F446RE pinout, and this one is the pinout diagram for the common cathode type 7 segment display. And you can clearly see in the top row of the 7 segment display, I am having 5 pins which are G, F, G2, A and B terminals. And in the bottom of the 7 segment display also, I am having 5 terminals nearly, that is E, D, G1, C and DP. And regarding the G1 and G2 that is available in the center terminals, these two are the common pins of the 7 segment display, so it will be internally sorted. So you can either use any one of the pin for connecting it to the ground of the circuit for displaying any number. And regarding all these 8 pins starting from A, B, C, D, E, F, G and DP, we can connect directly to any of the output pins of the microcontroller for driving the 7 segment display for displaying numbers from 0 to 9. And let me just show you the schematic diagram that I am going to build for displaying numbers in this 7 segment display. You can see this is the pinout diagram that I am going to build. That is, I am just going to connect A terminal of the 7 segment display to PA10, B terminal to PB3, C terminal to PB5, D terminal to PB4, E terminal to PB10, F terminal to PA8, G terminal to PA9 and finally DP I am just going to connect it to PC7. So these are all the pins that I am going to utilize in my microcontroller for driving this 7 segment display, that is common cathode type 7 segment display. And this is the schematic diagram that I am going to build. So let us try to configure all these pins in the CubeMX software as outputs for driving the 7 segment display, that is common cathode type 7 segment display. So from the schematic, it is pretty sure that these are the connections that we are going to make. So A terminal is connected to PA10, B terminal is connected to so and so, C, D, E, F, G, H, that is DP, all are connected to these respective pins. So from this connection details, we make sure that we are using GPIO-A, GPIO-B, GPIO-C for interfacing 7 segment display with our microcontroller. So as the first step, we just want to enable the clock of all these GPIO ports. So coming to our Keel Microvision IDE, first step that we are going to perform in the configuration segment is we are just going to enable the clock of all these pins. Of GPIOs enabled, that is GPIO-A, GPIO-B, GPIO-C. So I'm opening the user manual of the microcontroller STM32F446RE. So from the user manual you can clearly see this RCC AHP1 ENR is the register from which we can enable the clock of all the GPIO ports of the microcontroller. So in this particular register, this is a 32-bit register. We are having bits from bit 0 to bit 31. And bit 0 is meant for GPIO-A, bit 1 is meant for GPIO-B and bit 2 is meant for GPIO-C, and it goes on like this. So if I want to enable the clock of respective GPIO port, I just want to make that particular bit to be 1. If I want to disable the clock of any GPIO port, I just want to make that particular bit clear. So in our case, I just want these 3 bits to be turned on for enabling the clock of GPIO A, B and C of the microcontroller. So bit number 0, 1, 2 will be turned on for enabling the clock of GPIO A, GPIO B and GPIO C in our microcontroller. So this we have already done it. I hope you remember that. So let me just open this particular CMSys header file, and from the RCC structure you can clearly see the AHP1 INR register is provided with the name AHP1 ENR. Okay, this is the register which we are going to set the bit number 0, 1, 2 and 3. And let me just search for the pointer. I think the pointer name is RCC only. So I am searching this structure declared. You can clearly see the RCC base is mapped to the pointer RCC. So we can use this particular pointer for pointing to that register, and then we can set the bit number 0, 1 and 2 for enabling the clock of GPIO A, B and C. So RCC, I am just going to point to AHP1 ENR is equal to RCC pointing to AHP1 ENR R of 1 left shifted by 0 for setting bit number 0 and 1 left shifted by 1 for setting the bit number 1 and 1 left shifted by 2 for setting the bit number 2. So this particular line will enable the clock of GPIO A, B and C. And as the next step, I just want to configure all these pins which are connected to the 7-segment display terminals to be output pins. So PA10, PB3, PB5, PB4, PB10, PA8, PA9, PC7 must be configured as output pin in our microcontroller. So that is the next step that I am going to do. So all 7-segment terminals must be made output. So in the user manual, let me just open the register required for that. In the GPIO peripheral, let me just open the GPIO peripheral, GPIO general purpose input output. So this mode R is the register which is useful for configuring the particular pin as input or output in our microcontroller with help of the respective pointer for the GPIO port, so and so like GPIO A, GPIO B, GPIO C, etc. So this is also a 32-bit register. It is having bits from bit number 0 to bit number 31, and in this register you can clearly see 2 bits is useful for configuring one particular pin. That is, for example, bit number 0 and 1 clubbed together will configure the pin number 0 in that corresponding port, and bit number 2 and 3 will configure the pin number 1 in our corresponding port. The bit status of 2 bits clubbed together will configure the corresponding port pin. So if I want to configure the pin number 2, I just want to set the corresponding values in bit number 4 and 5 of this register, and so on. So you can clearly see writing value 0, 0 to any of these 2 clubbed bits will configure that particular pin as input, and writing value 0, 1 to any of these 2 clubbed bits will make the corresponding pin as general purpose output pin, and writing 1, 0 will configure the pin in alternate function mode, and 1, 1 will configure the pin in analog mode. That's it. So these are the 4 types of configurations that is possible for each pin. So in our case, I just want the pin to be configured as output, all the pins to be configured as output. So let me just open this So in port A, I just want 10th pin, 8th pin, 9th pin. That is port pin PA8, 9 and 10. I need it to be configured as output. For configuring the PA8, that is 8th pin of the port A, I just want to write 1 to 16th bit number and 0 to 17th bit number. And for configuring the PA9, that is the 9th pin in our port A, I just want to write 1 to 18th bit in the register and 0 to 19th bit. And for configuring the 10th pin, that is the PA10, I just want to write 1 to 20th bit number and 0 to 21st bit number. Since all the initial value of these ports are 0, you can neglect the step of clearing the port pins and you can perform only the setting operation in the respective ports. So for configuring PA10, PA8 and PA9, I just want to write data to bit numbers from bit 16 to bit 21 in this register. So I just want to write 1 to 16, 18 and 20 for configuring PA10, 9 and 8 pins as output. So I'm just going to use the pointer GPIOA and I'm going to point to mode R register is equal to GPIOA mode R of 1 left shifted by 16, R of 1 left shifted by 18, R of 1 left shifted by 20. So when I write values of 1 to 20, 18 and 16th bit of these three registers with the help of GPIOA, the pin number PA10, PA8, PA9 will be configured as output. So that is the expectation. So in this line I am making PA10, PA9 and PA8 as output. And regarding the PB port, I just want to configure PB3, 4, 5, 10 to be configured as output. So 3, 4, 5, 10. So for configuring the third pin of the port as output, I just want to make this particular sixth bit in this register high and 7th bit in this register to be low. And for configuring the fourth pin in the port to be output, I just want to set this particular 8th bit high and 9th bit low. And for configuring the 5th pin as output, I just want to set this particular pin as high, that is the 10th bit as high and 11th bit to be 0. And finally for setting the 10th pin as output, I just want to set the 20th bit as high and the 21st bit as low. So for configuring 3, 4, 5 and 10th pin as output in port B, I will be using the pointer GPIOB and I will be setting the bits such as 6, 8, 10 and 20th bit in this register for setting those for configuring those 4 pins as output. B 6, 8, 10, 20. So this will configure PB3, PB4, PB5 and PB10 as output. And finally, for configuring the PC7 as output, I just want to use the pointer GPIO-C and I want to set this particular bit number 14 in this register high and clear 15 in the same register. So I am just neglecting the clear operation and I am going to set to the GPIO-C mod RF by 14. So this will configure PC7 as output. So the output configuration is done for all the pins which are connected to terminals of the 7-segment display. We have configured all the pins which are connected from our microcontroller to the 7-segment display anode terminals as output pins. Now let us just write one function which is useful for converting a byte of data, that is converting a 8-bit byte of data into individual bit and then turning on the respective pins as per the each bit status available in that byte of data. That is, let us just write to be void print data is the function name, and I am just going to receive a parameter for this function with the name of data. So now to this function I am just going to pass a parameter called data. So this data will be this data variable will be a 8-bit hexadecimal data. So we will be passing a 8-bit hexadecimal data as the parameter to this function, and what this function does is that it will split the 8 individual bits available in this hexadecimal data, that is starting from bit 0 to bit 7, and according to the each separate bit status we will turn on the respective pins as per the bit status. That is, if we are having 1 as the value of bit number 0, we will turn on the corresponding pin that is representing the bit number 0, and if it is having 0, we will turn off the same pin. So that is the purpose of this function. So firstly what I will do is I am just going to check for the condition data ampersand of 0x01. So now what happens is I am just going to check whether the 0th bit is turned on. So if it is turned on, what I will do is I will turn on the pin representing bit 0, else I will turn off the pin representing bit 0. So this is what we are just going to do. We are just going to check whether the 0th bit is high. If it is high, I will turn on the pin which is representing the bit 0, and if this condition is false, that is if the bit is having the value 0, we will turn off the same pin which is represented for the bit number 0 in that corresponding byte. So this is what we are just going to do. So how this works is that, let me just take one example. Let us assume that the data parameter that we are passing to this function is having the value 0x3e. So this is the value that I am having, or which I am passing as a parameter to this function. So data ampersand of 0x01 is that data is nothing but 0x3e. So 0x3e ampersand of 0x01 will be performed. So 0x3e is nothing but in 8-bit. Let us write this 3e in 8-bit binary format: 00111110. So this is 0x3e, and 0x01 is nothing but 00000001. So if I perform AND operation between these two bytes of data, the result will be 00 will be 0, 00 will be 0, 0, 0, 0, 0, 0, and we are having 1 only in the 0th bit. So 0 ampersand of 1 will provide me 0. So the 0th bit is 0. So this condition will be failed, and I will be getting, or I will be turning off the pin which is representing the bit number 0. And if I want to check for the bit number 1, so this is representing the bit number 0 of the byte, and if I want to check for the bit number 1, what I can do is I can perform AND operation of the same data with 0x02, and if I get the result of 0x02, that means the bit number 1 is turned on. So I'm just going to turn on the pin representing bit number 1, else I will turn off the pin representing bit number 1. So now you can see 0x02 is performed. So 0x02 is nothing but 10 in binary, and if I perform this operation, that is 0x3e ampersand of 0x02, I will get 1 ampersand of 1 to be 1. As we know the AND table, AND truth table, I will be getting the result 1 if only both the inputs are 1. Other than that, any combination 00, 10, 01 will be fetching me the output 0. So that is the AND table, right? So I will be getting 0x20 as the result. You can see here, this is the binary equivalent for 0x20. So this condition will be true. So the pin that is representing the bit number 1 will be turned on. And if I check for the bit number 2, so that can be done by performing AND operation of this data with 0x04. If I get 0x04 as the result, I will be turning on the pin representing the bit number 2. Else I will be turning off the same pin which is representing the bit number 2 in the byte. So now you can see 0x40 is 100. So if I perform AND operation of this, you can see 1 ampersand of 1 will give me the result 1. Other than that, all the bits will be 0. So I am getting the result 0x04. So this condition will be true. So this pin will be turned on if I pass the value 0x3e as the data to this parameter. And if I want to check for the bit number 3, what I can do is I can perform AND operation of this data with 0x08, and if I receive 0x08 as the result, I will be turning on the pin which is representing for the bit number 3, or I will be turning off the same pin which is representing the bit number 3 in the byte. So this one is meant for 0th bit, first bit, second bit, third bit. So now you can see this is the third bit checking condition. So 0x08 is this one, and if I perform AND operation of this data with 0x3e, which is the example data passed, I will be getting the result 1 ampersand of 1 in this position. So 1 ampersand of 1 is 1. Other than that, I will be getting all the values to be 0. So the data that I am going to get is 0x08. So this condition will be true, so the pin will be turned on, which is corresponding to the bit number 3. And next I am just going to write for fourth bit. So for checking for fourth bit, I am just going to perform AND operation of this data with 0x10, and if I receive 10, I will turn on the bit which is representing, I will turn on the pin which is representing the fourth bit, or I will turn off the same pin. So now let's take the same example for checking the fourth bit. Now you can see clearly 1 ampersand of 1 will provide me the value 1. Other than that, I will be getting all the values to be 0. So now I am getting the result to be 10. So this condition will be true, so the pin will be turned on in this fourth bit check condition. And now I am just going to check for the fifth bit. So for checking for the fifth bit, I can perform AND operation of this data with 0x20. If I get 0x20 as the result, I will be turning on the fifth bit, or I will be turning off the fifth bit pin. So 0x20 is nothing but, so this is the 0x20, and if I perform AND operation of this 0x3e example data byte with this 0x20, you can see 1 ampersand of 1 will provide me 1. Other than that, I will be getting all the bits to be 0. So I am getting the result to be 0x20. So this condition is true, so the fifth bit corresponding pin will be turned on in my example case. And if I check for the sixth bit, I just want to perform AND operation of this data with 0x40, and if it is, or if the result is 0x40, I will be turning on the bit which is representing the sixth bit, or I will be turning off the sixth bit. Similarly, I am just going to perform or check for the seventh bit by performing AND operation of this data with 0x80. If the result is 0x80, I will turn on the seventh bit. I will turn on the seventh bit, or I will turn off the seventh bit. So you can clearly see 0x40 is nothing but 10, and now what happens is 0 ampersand of 1 will provide me 0. So I will be getting 0x00 as the result of the sixth bit check condition for this example byte of data 0x3e. So this condition will be false. So the pin which is corresponding to the sixth bit for this application byte will be turned off by executing this else part. And nextly, we are just checking for the condition of data ampersand of 0x80. So 0x80 is 10000000. So if I perform AND operation of this data with example byte 0x3e, what I will get is 1 ampersand of 0 is 0. So now also I will be getting the value 0x00 as the result. So this condition will be false in the seventh bit condition. So the else part will be executed, turning off the pin which is corresponding to the seventh bit in the parameter byte of data. So we have completed the function. Now you can see clearly this function is useful for converting a byte of data sent as a parameter to this function into separate bits starting from bit 0 to bit 7, and then based on each bit status, whether it is 1 or 0, the pin which is corresponding to each of the bits will be turned on or off. So based on the status of the bits available in the byte of data sent as parameter, the each pins which is corresponding to that separate bits will be turned on or turned off. So that is the purpose of this function. We are just going to use this function for interfacing several devices like 7-segment, LCDs, etc. So we will be using this function in several of our lectures from now. So now I'm just copying this function and I'm pasting it right above this main and below this header call. So this A terminal is PA10, B terminal is PB3, C terminal is PB5, D terminal is PB4, E terminal is PB10, F terminal is PA8, G terminal is PA9, and a DP or H terminal is PC7. So this is the connection that we have made in the hardware for interfacing the 7-segment with our STM microcontroller. So first step that we want to do is we just want to turn on this particular pin right over here if the bit is set, and we just want to turn off this same pin if that is not set. That is the use case. So GPIO A pointing to ODR, which is the data register of the microcontroller. R is equal to 1 left shifted by 10. So let me just show you this ODR register. So output data register is a 16-bit register. It's a 32-bit wide register, but upper MSB 16 bits are masked. You cannot use this. It is reserved, and only you can access the lower LSB bits, 16 bits, starting from bit number 0 to bit number 15. So if I want to make a particular pin as high, I just want to make the respective bit number as 1 in this register, and if I want to make a particular digital pin as low, I just want to clear the same bit number in this register. For example, if I want to turn on the PA0, I just want to use the pointer for GPIO A and I want to make this bit number 0 of this register 1. If I want to clear the same pin, or if I want to make the PA0 pin low, I just want to clear the bit number 0 in this register. So this is what the expectation is. Now I'm just going to clear the same pin. Ampersand is equal to negation of 1 left shifted by 10. So similar fashion, I'm just going to perform the same things right over here. In this portion, I'm just going to set the third bit in GPIO B, and here I'm just going to clear the same third bit in GPIO B ODR register. Here I will be setting the bit number 5 in the ODR with the help of GPIO B pointer, and here I will be clearing the same bit number 5 in the ODR register with the help of GPIO B pointer. And here also I will be clearing the bit number 4 in the ODR register with the help of GPIO B pointer. And here I will be setting the bit number 4 in the ODR register with the help of GPIO B pointer. Here I will be setting the 10th bit with the help of GPIO B pointer for ODR register, and here I will be clearing the same 10th bit. Here I will be taking the A configuration, port A configuration for setting the pin number, bit number 8. And here I will be clearing the pin number 8, and here I will be clearing the pin number 9, and here I will be setting the pin number 9. And finally here I will be using the GPIO-C pointer for setting the 7th bit for turning on the 7th pin, that is a PC7, and here I will be turning on the same PC7 if this condition is failed. So I have altered this function. You can clearly see this function or this condition is meant for PA10, and this condition is meant for PB3, and this condition is meant for PB5, this condition is meant for PB4, this if else condition is meant for PB10, this is meant for PA8, this is meant for PA9, and this is meant for PC7. So now this particular pin data function will be useful for writing the data to data lines of 7-segment display. So the data that we want to write is, we have already found out that in previous one of our video, that is 7-segment display working explained, where I have explained you how to derive the hexadecimal values for common anode and common cathode type 7-segment display. So this is the derivation for common cathode type 7-segment display. So writing 0x3f to the port pins of the 7-segment will print number 0 on the 7-segment. This will print number 1 on the 7-segment. This will print 2, 3, 4, 5, 6, 7, 8 and 9. Let me just copy this, and I am pasting it right over here. So what I can do is I can just print data. I can call this function and I can write like 0x3f. So when I write like this, after that I will provide a delay of let's take it to be 5 lakh. Okay, I have not defined the delay function, so I am just defining the loop delay function long of t while of d minus minus. So when I write like this, the number 0 will be printed on the 7-segment display, and the program will wait here for a certain rough delay. After that again this will be executed. So after this I am just printing the number 1 to the 7-segment display. So after the number 1 I am just going to print number 2 right over here, and then number 3 right over here. After the number 3 I am just going to print number 4, 5, 6, 7, 8 and 9. So the logic is very simple. What happens here is the number 0 will be printed, and the display will be holding the number 0 until this delay is complete, and after this delay is completed the number 1 will be printed, and the 7-segment will be waiting with the number 1 until this delay is complete. After the delay the number 2 will be printed, again it will be waiting here, and number 3 will be printed, again it will be waiting here for the same delay, and 4 will be printed, delay, 5 will be printed, again delay, 6 will be printed, again delay, 7 will be printed, and again it will be waiting here, and 8 will be printed on the 7 segment, again delay, 9 will be printed on the 7 segment, and again delay. Once this delay is complete, it will come right over here. This is the first line inside the while of 1, since this is a infinite loop. After reaching the end of the loop, it will come again to the starting of the loop. So again the number starts from 0 and it will count till 9. So this is the logic. The 7 segment display which is connected to the port pins of the STM32F44RE microcontroller will be printing numbers from 0 to 9 for a certain rough equal delay intervals, and again it will start moving from 0. So this continues until the microcontroller is stopped. So this is the logic that we have written. I'm just building this code. Just click on F6 or F7. Just click on F7 in your keyboard or this particular icon for building the project. You can clearly see we found 0 errors in our program. So let us try to dump this program to our microcontroller and see whether it is working properly or not as per our expectations. So I have already built the schematic that I have already shown you before in the initial segment of this video in a breadboard with the help of Nucleo F444RE development board. So let us visualize the output in the hardware. Now you can see this is the common cathode type 7 segment display, and this is the pinout structure of this common cathode type 7 segment display. So on the top we are having 5 pins and on the bottom we are having 5 pins. And the center terminal in the top and bottom are the common pins, and we can use either one of these 2 pins. And you can see in a breadboard I have connected the 7 segment display, that is the common cathode type 7 segment display, and to the center terminal I have connected a 220 ohms resistor, and I have connected that 220 ohms resistor to the breadboard rail right over here, which is the common pin. And the bottom common pin I'm not going to utilize it, and other than that I have connected 8 jumper wires, that is the male to female jumper wires starting from terminal A to terminal H. So I'm just going to make the connection between the 7 segment display and my STM32F444RE microcontroller through this Nucleo F444RE development board. So this is the terminal A. I'm just going to connect this terminal A to the pin PA10. And regarding the terminal B, I'm just going to connect the terminal B to the pin PB3. And then C will be connected to PB5. So here is the C. Here is the C. I'm just going to connect the C terminal to PB5 of STM32F444RE. And D will be connected to PB4. So here is the D. I'm just going to connect this to PB4. Sorry. C. And this one is D. And regarding the E terminal, D. And regarding the E terminal, I'm just going to connect it to the pin PB10. And F, I'm just going to connect it to, here is the F. So here is the F. I'm just going to connect this F terminal to PA8, and the G terminal I will be connecting it to PA9, and finally the H terminal, that is the dot pin, I'm just going to connect it to PC7. So that's all about the circuit connections that we want to do. Now you can see this is the output which I got in my hardware after building this circuit in the breadboard. The LCD display, that is the common cathode LCD display, is displaying numbers from 0 to 9 at a time interval of 1 second for each number, and when it goes beyond 9, again the number rolls over to 0 and the process continues. So the program is working fine as per the logic that we have written. And we successfully interfaced the common cathode type 7 segment display to our STM32F44RE microcontroller. See you in the next video. Thanks for watching. So this is the output that we got in the hardware. I hope you learned to develop the drivers required for interfacing 7 segment display with our microcontroller STM32F446RE microcontroller in this video. See you in the next video. Thanks for watching.